Hello everyone, welcome back to the Atharva Academy. Myself Chinmay Dhoduk. In previous video, we have discussed some example based on thermal stress and thermal strain. Now in this video, we are going to discuss more example of thermal stress and thermal strain. Here, this is first example that we are going to discuss today. Here bars are in series. You can see bar 1 and bar 2 is connected in series. And here we fixed left hand side of this bar 1, and at the right hand side we have given small gap of distance lambda, and here there is restriction at distance of lambda from this surface. Fine. Let's say here we increase the temperature of both this bar delta T, and due to this increase in temperature, what is the value of thermal stress and thermal strain in these bodies? This example is going to be the nearly same example as discussed in previous video. It is the case of partially restricted body, but only difference is that here there are two bodies instead of one body. Fine. Now here we are going to use same approach as discussed in previous video. Here also there will be two cases. In case 1, let's say total change in length of both the bar is greater than lambda, means total change in length due to this temperature difference is greater than lambda, means this surface is exceeding this restriction, means this surface will move to this point if there is no restriction here. And in second case, we will consider that change in length of both this body due to increase in temperature delta T is, let's say delta T is less than or equal to lambda, means this surface is not exceeding this fixed surface, or we can say this restriction, means this surface will move, let's say up to here. So we know that this case will be the case of free expansion, because there is no restriction to change in length of these bodies, right? So in this case, value of stress will be 0. And we can say that this condition is condition of zero stress, because when delta T will be less than or equal to lambda, value of stress will be 0 in these bodies. Fine. Now in this case, value of deformation will not be 0. What will be the value of deformation here? Value of deformation delta T will be equal to deformation in body 1 due to increase in temperature delta T plus delta T2, that is deformation in body 2 due to increase in temperature delta T, and it will be equal to L1 alpha 1 delta T plus L2 alpha 2 delta T. Here L1 and L2 is length of bar 1 and bar 2 respectively, and alpha 1 and alpha 2 is coefficient of thermal expansion in body 1 and body 2 respectively. Fine. So if delta T is less than or equal to lambda, then there is no stress and value of deformation is this. Fine. Now we are going to discuss second case in which delta T is greater than lambda. Now if delta T is greater than lambda, then this surface will move up to, let's say, this distance, and here this total distance will be delta T. Fine. It will be total of delta T1 plus delta T2, and this deformation is due to increase in temperature delta T. So here it is delta T. Now we know that there is restriction at distance of lambda from this surface, so this body will not allowed to deform beyond this restriction. So what we are going to do, we are going to apply reaction force at this surface in this direction. Let's say it is having value R, and due to that we will deform these two bodies up to this restriction, means by applying this load we will deform these two bodies up to this surface. And here this deformation will be deformation delta R, means deformation due to this reaction R. So what we have done? First of all, we have increased the temperature delta T of both this body 1 and 2. Due to that, we allowed these bodies to deform up to this surface. And then we apply restriction, or we can say one compression load R in this direction, and we deform these bodies up to this surface. Now here you can see that this delta T is equal to this lambda plus delta R. Fine. Here this total distance is delta T, and it is summation of this distance, that is lambda, plus this distance, that is delta R. And here we are only considering magnitude of this deformation. Fine. So we have this equation, and we know that delta T is equal to delta T1 plus delta T2, and that is equal to L1 alpha 1 delta T plus L2 alpha 2 delta T. So here I will write L1 alpha 1 delta T plus L2 alpha 2 delta T, which is equal to lambda plus delta R. Now what will be the value of delta R? Means what will be the value of deformation in both the bodies due to this reaction R? It will be summation of delta R1 plus delta R2. Means deformation in body 1 due to this reaction, deformation in body 2 due to this reaction R. Fine. Now we know that deformation in body due to axial load is delta is equal to PL by AE. Fine. So here we can write that it is equal to lambda plus P1 L1 divided by A1 E1 plus P2 L2 divided by A2 E2. Now how we are going to find out value of P1 and P2? For that we will use same method. To find out value of P1, we will take section in body 1, and we will take sum of forces acting in that body either side of this section. And here you can see there is only one load acting at the right side of this section, and that is this reaction R. And it is acting towards this section, so we have to take this reaction as negative. P1 will be equal to minus R, right? But here we are only considering magnitude, so we will take this R as positive. And now what will be the value of load P2 in body 2? For that we will take section in body 2, and we will take sum of forces acting on that body either side of this section. And here we will take right side of the forces, and that is same R acting on this body. So it will be P2 is equal to minus R. And similarly we will take this reaction as positive because we are only considering magnitude. Fine. See, you can also understand that this delta R is deformation in bodies due to this reaction, and this deformation is negative, right? Because we are decreasing the length of these bodies. So actually we have to take negative sign here for both this deformation, and we should also take these values negative here. So if you will take negative sign here and you will use minus R sign, then finally you will get plus sign, right? Because negative into negative will be positive, right? So you can also understand like that. Now in the question, most of the values will be given to you. Only you have to find out value of reaction, because reaction will not be given to you. So you can put this reaction here instead of this P1 and P2, and from this equation you can find out value of R, right? And once you have value of R, you can find out value of thermal stress in these bodies. Thermal stress in body 1 will be sigma 1 is equal to R divided by A1, and thermal stress in body 2 will be equal to R divided by A2. And remember that this load is actually compressive load. So finally you have to take this stress as compressive stress, means you have to write negative sign here. Fine. So this will be the value of stress in these bodies. Now we will discuss this next example in which we have composite bars which are in parallel connection. Here you can see that this is bar 1 and this is bar 2. These both are fixed at this left end and these both are connected at this surface. Length of both this bar is L. Now we are going to increase temperature delta T of both this body uniformly. Due to that, what is the deformation in these bodies and what is the value of thermal strain and thermal stress in this body. Now let's say coefficient of thermal expansion of body 1 is greater than coefficient of thermal expansion of body 2. Means if we increase temperature delta T of both this body, then there will be more elongation in body 1 than elongation in body 2. Means here we can write that delta T1 will be greater than delta T2. First of all, let us assume that these both bodies are not connected to each other. So if we will increase delta T temperature, then this body 1 will deform, let's say up to here. And here this is the deformation in body 1 due to increase in temperature delta T, delta T1. And let's say due to this increase in temperature delta T, this body 2 elongate like this. Here deformation in body 2 due to increase in temperature delta T should be less than delta T1, right? So here this deformation is delta T2. Now here this is the deformation in body due to increase in temperature delta T. It is different because we assumed that at this time these both bodies are not connected to each other. But what would happen if these both bodies are composite bars? Means these both bodies are connected to each other. If these both bodies are connected to each other, then deformation in this both the body will be same. Means displacement of this end of both the bodies will be same, and that deformation will be in between these two values delta T1 and delta T2. Fine. So let us assume that deformation in both the bodies is up to this surface. Means this body 1 will try to deform the body 2 up to this surface, and this body 2 will try to restrict the deformation in body 1 up to this surface. Means this body 2 will not allow body 1 to deform beyond this surface. So what would happen? This body 2 will try to apply reaction on body 1 in this direction, and this body 1 will try to apply reaction on body 2 in this direction. Means this both body will apply reaction on another body. Fine. Now let us take value of this reaction R. It will be same for both the bodies, right? Now due to this reaction, deformation in body 1 will be this much, and let's say this deformation is deformation delta R1, means deformation due to this reaction. And here in body 2 there will be this much amount of deformation due to this reaction, right? And let us take this value of deformation as delta R2, means deformation in body 2 due to this reaction. Now understand that deformation from here to here, it will be delta R1 plus delta R2, right? So here I am going to write delta R1 plus delta R2, and it will be equal to delta T1 minus this delta T2, right? Here from this point to this point it is distance delta T1, and from this point to this point it is distance delta T2. So delta T1 minus delta T2 will be this much deformation, that is shown as yellow color. Fine. So we can write this equation. Now we know that delta R1 is RL by AE plus delta R2 is RL by AE. Here this length is same for both the bodies and area and young modulus may be different. So we will take A1 E1 here and A2 E2 here, and it will be equal to, what will be delta T1? Delta T1 will be L1 alpha 1 delta T minus it will be L2 alpha 2 delta T. Here length is same, so we will take L here. So we have this equation, and in this equation all the values will be given to you, only value of reaction is need to be find out. So from this equation you can find out value of reaction, and once you have value of reaction you can find out value of sigma, that is stress in body 1, and it will be R divided by A1, and you can find out value of stress in body 2, that is R divided by A2. Here you have to take value of R positive. Fine. Now once you have value of stress, you have to take stress in body 1 as negative, because reaction in body 1 is compressive. So there will be compressive stress in body 1, and reaction in body 2 is tensile. So there will be tensile stress in body 2. So we will take this stress as positive stress. Fine. So I hope that you understand how to find value of thermal stress in this type of case. Now we are going to discuss this next example, in which this body is restricted on 3 sides, and in which we are going to find out strain in this direction. We are going to take this direction as x direction and this direction as y direction. So we have to find strain in x direction. Now here this dimension of this body is, let's say, L, and this dimension of body is also, let's say, L, and we are going to increase temperature of this body delta T. Now what will be the value of change in dimension of this body in this direction, and what will be the value of strain in x direction? We have this same body here, and we are going to increase delta T temperature of this body, and due to that, if there is no restriction in this body, then change in dimension of body will be like this. Fine. There will be strain in x direction, and also there will be strain in y direction. Here strain in x direction will be thermal strain, and it will be alpha delta T, right? And similarly strain in y direction will be epsilon Ty is equal to alpha delta T, that we have discussed earlier, right? And here we know that body is restricted on 3 sides, and it is only allowed to deform in x-axis in this direction. Means here this strain is not permittable. So we are going to apply compressive load in this direction, and we will deform this body up to its initial state, this. So if we are going to apply this compressive load, then dimension of this body is going to be decreased in this direction like this. Fine. And if dimension in y direction decreases, then we know that dimension in x direction is going to be increased. So it will be like this. Fine. So this deformation, or we can say this strain, is due to this reaction. And let's say here strain in y direction is epsilon r y, means strain due to this reaction R. And from this figure we can understand that value of this strain will be equal to this strain, which is strain due to temperature difference delta T in y direction. So it will be alpha delta T. But it will be negative because here dimension is decreasing, right? So here magnitude will be same but direction will be opposite. So we will take negative sign here. Now we know that equation of Poisson's ratio mu is lateral strain divided by linear strain. Here lateral strain will be in this direction and linear strain will be in this direction. This direction is taken as linear direction because we apply reaction in this direction. So here Poisson's ratio will be minus lateral strain, that is strain in x direction, and that is epsilon r x divided by strain in y direction, that is epsilon r y. Fine. So from here we can find out value of strain in x direction due to this reaction. So here this epsilon r x will be equal to minus mu epsilon r y, and we know value of epsilon r y, it is minus alpha delta t. So from here it will be epsilon r x is equal to mu alpha delta t. Here minus 1 into minus 1 will be plus. Fine. Now what will be the total strain in x direction in this body? It will be summation of these both strain, right? So we can write that here this epsilon x will be equal to epsilon t x plus this epsilon r x. Here this epsilon t x is strain in x direction due to increase in temperature delta T, and this epsilon r x is strain in x direction due to this reaction applied in y direction. Fine. So it will be equal to alpha delta T plus mu alpha delta T, and we will take alpha delta T common. So it will be 1 plus mu. Fine. So finally we have strain in x direction, and we know that strain in x direction will be change in dimension in x direction. Let's say change in dimension in x direction is delta L divided by original dimension in x direction is L. So from here we can find out value of delta L. It will be this L multiplied by alpha delta T into bracket 1 plus mu. Fine. So I hope that you understand how to find value of strain in this type of body. This example is not important as per the GATE point of view, but I have given you this example for your better understanding. Fine. So today in this video we are going to stop here, and we will continue in the next video. Till then, stay motivated and happy practicing.